Imagine a robot that doesn't wait for commands. It reads the track, spots obstacles, and chooses its next move. In this project, we'll turn an ESP32 into a small autonomous robot that can sense, decide, and drive on its own. Before we build, let's connect the dots. You already know the ESP32, basic circuits, outputs, sensors, servos, motors, and Bluetooth control. Project 7 brings those skills together so the robot can sense distance, make decisions, and move without direct human control. Previously, your robot was a follower. A person pressed forward, left, right, or stop, and the robot obeyed through Bluetooth. Now the control source shifts from the human to the robot itself. Sensors help it notice the track and detect obstacles, while the program decides whether to keep going, turn, stop, or recover. That loop is the core idea of autonomy. Sense, decide, act. Simple, but real robotics. Think of the robot as a sense, decide, act system. The IR line sensors tell it whether each side is seeing dark tape or a lighter floor. The ultrasonic sensor measures distance to obstacles ahead. The ESP32 collects those signals and runs the logic for following the line, turning, stopping, or avoiding something. It does not drive the wheels directly, though. It sends commands to the motor driver, which supplies the power needed to spin the left and right motors. Power keeps both the controller and driver running. An infrared line sensor is basically asking one question: how much of my light came back? It shines invisible infrared light downward, then measures the reflection. A light floor usually bounces more light back, while a dark line absorbs more, so the reading changes. With multiple sensors across the front, the robot compares those readings. If the dark line is centered, it keeps going. If the dark reading shifts left or right, the robot corrects its steering. That reflection difference becomes navigation information. A line follower does not know the line's position directly. It infers position from sensor patterns. If the center sensor sees the line, the robot can keep moving forward. If the left sensor detects the line, the robot has usually drifted too far right, so it turns left to recenter. If the right sensor detects the line, it has drifted too far left, so it turns right. When no sensor sees the line, the program should enter recovery behavior, such as slowly searching until the line is found again. Calibration starts with real conditions, not ideal ones. Place the robot on the light background and record the reading. Then place it on the dark line and record that value too. Pick a threshold between the two, so readings are classified consistently, depending on your sensor. Keep the sensors close to the floor, but high enough to avoid scraping. If lighting, battery level, surface material, or track color changes, recalibrate before testing again. An ultrasonic sensor works a lot like echolocation. The ESP32 briefly triggers the sensor to send out a high-frequency sound pulse. If there is an object ahead, the sound reflects back as an echo. The sensor reports how long that round trip took, and the ESP32 converts the time into distance. A short delay means the object is close. A longer delay means it is farther away. When the distance drops below a safe threshold, the robot can stop, slow down, or choose a new path. Sensor fusion means the robot does not rely on one clue by itself. Think of a student crossing a busy hallway. Their eyes check where to walk, their ears notice danger, and their brain decides whether to keep moving or stop. Here, the IR sensors tell the robot where the line is. The ultrasonic sensor tells it whether an obstacle is ahead. The ESP32 combines both answers before choosing a movement. Instead of blindly following a line into a cone, the robot follows the path while reacting to the world around it. When several sensors report at the same time, the robot needs a clear order of importance. The first question is safety. Is something too close? If yes, the robot stops or avoids it, even if the line sensor still sees the track. If the path is clear, line following becomes the next priority. If no line is detected, the robot switches into recovery mode and searches. This priority order prevents mixed commands and makes the robot's behavior predictable. Autonomous behavior is built from small if-then rules. Each rule reads a sensor pattern, then chooses a motor response. If the line is centered and the path is clear, the robot drives forward. If the line shifts left, it gently turns left. If it shifts right, it gently turns right. If an obstacle appears, it stops or waits. And if the line disappears, it slows down and searches in small movements until the sensors find the line again. Together, these simple rules create reliable navigation. In code, the program works as a loop. Read the left, center, and right IR sensors. Turn those raw numbers into states, then choose a motor response. Rather than letting every sensor value directly control the wheels, compare each reading with a threshold. That gives you clearer conditions like center sees the line or left sees the line. Then the if, and else blocks decide what happens next. For smoother tracking, avoid stopping one wheel suddenly. Use small speed differences so the robot corrects gently and stays stable. Before the robot continues following the line, it should ask one safety question. Is anything too close? The ultrasonic reading is compared with a minimum distance, often around 10 to 20 centimeters, depending on speed. If the reading is smaller, stop both motors immediately. From there, the simplest behavior is to wait until the path clears. A smarter behavior is to reverse slightly, turn around the object, and then search for the black line again. Once the line is detected, the robot returns to normal line following mode. This keeps obstacle handling safe, predictable, and recoverable. Robots almost never run perfectly the first time, so treat problems as clues. If movement is shaky, slow the robot down before changing anything else. Then adjust turning strength until it follows curves smoothly. If it loses the line, recalibrate the sensors and check their height above the surface. If obstacles are missed, inspect the ultrasonic wiring, sensor angle, and distance threshold. Test in stages. Line following first, obstacle detection second, and then the combined program. Change one setting at a time, or you won't know what fixed the issue. You've now built a robot that can make local decisions on its own. IR sensors help it follow a path. Ultrasonic sensing helps it avoid obstacles, and the ESP32 combines those inputs with motor control rules. That is the foundation of autonomy. Next, we'll connect that intelligence to the world with Wi-Fi and ESP32 IoT robotics.